Alright, I just went through a video where I did the standing wave pattern on a string that was fixed on either end. What I'm going to do now is talk about an air column. I'm going to do the closed air column and the open air column, hopefully all in one video here. And I'm going to go a little bit faster because, like I said, I just did the fixed string one. So closed air column. Closed air column means that it is an air column which is open on one end and closed on the other. I would suggest you think of something like a pop bottle. When you've drank part of the pop out of it, then you go and blow across the top of the pop bottle and it makes a noise. What you have here is you have a fixed end reflection on one side and a free end reflection on the other side. To create a standing wave in this environment, what you need is a node on the end of the fixed end and an antinode on the free end. We're going to assume that this column is length L long. Again, I'm going to draw a sine wave over here to help myself. And in the first situation, I'm going to imagine going from the node to the very first antinode. So my pattern would look something like this. Now, again, it's an arbitrary choice. I could have drawn it going down as well, but I happen to draw it going up. What that means is the first geometry that will lead to a reflected wave that is in phase with or adds constructively to the incident wave is when the length of the air column matches 1/4 of a wavelength. That's just the first quarter of this whole wavelength. Going to the next example. Here we're going to start at a node again. We're going to go to an antinode and then go back down to the next antinode, so down here. So this pattern would look like this. Again, this now is a half and 1/4 of a wavelength. So this length is 3/4 of a lambda. This would be the n equals 1 condition. Most of the sound produced would be produced at this harmonic, the first harmonic or the fundamental frequency. This would be the n equals 2, or the first overtone or the second harmonic. Again, we go from a node to an antinode. Finally, I'll do the n equals 3, and then we'll look at the pattern and talk about how to put that into an equation. Here, again, I'm going from a node to an antinode. Looking at my sine function, I did that one. I did that one. So now I'm going to go one more up to the next antinode. So this pattern looks like this. Like that. And if we think this is one full wavelength plus 1/4, so what we're dealing with is 5/4 of the wavelength. It's pretty easy to see the pattern here, 1, 3, 5. But if we want to put that into a general equation, we could say that 2n minus 1 divided by 4 times lambda is the general relationship that will relate the length of an air column to the wavelengths produced by the n equals 1, 2, 3, or whatever n value you want for that closed air column. An open air column, alternatively, is one that is open on both ends, so both ends result in free end reflections. This could be like a tube. A common example of this would be a flute, where a flute has holes on one end and you blow across the top of another hole. What that means, since both ends are free, is that we need an antinode on either side. Again, I'll use a sine function to help me come up with my answers. This time, though, I have to start from an antinode and go to my next antinode. So my first pattern looks like this. Arbitrarily chosen, I could have started from the bottom and gone to the top, but the relationship is the same. If this is the length of the air column, this represents 1/2 of a wavelength. See, there's a quarter missing here, and there's another quarter missing here. So that's half of the wavelength. So in this case, the length is equal to lambda over 2. that would be the n equals 1, the simplest, fundamental, first harmonic associated with an open air column. The second pattern has a starting and an antinode. We went to that antinode for the first pattern, so we've got to go back up to this antinode for the second pattern. This now represents one full wavelength, and so the length of this air column is the same as the wavelength. That's for the n equals 2 case. First overtone, second harmonic. In this case, again, as I did in a previous video, I'm going to call this 2 lambda over 2 because I know the answer and I'm trying to make it clear what the pattern is going to look like. Go from an antinode to another antinode. Here are my nodes, by the way. All right, I'll do one more. The n equals 3. Here I've done the one where I go down and back up. So all I have left to do is go back down one more time to the next antinode available. Looks like that. And if this is a full wavelength, and this is another half, this works out to be 3 lambda over 2. Again and again, antinodes. Looking at these and remembering it from our fixed string, we should be able to see that the length of the air column is equal to n lambda over 2, or the length of the air column will be equal to those wavelengths being able to produce standing waves on that air column. Here again, n equals 1, 2, 3. And as I said in the previous video, the vast majority of the power would be produced at the n equals 1 level, unless, for example, as somebody who plays the flute would have the ability to do, you only create a vibration at the n equals 2 level, in which case you could make the n equals 2 level be the one that was observed instead of the n equals 1. So that is something that a skilled musician might have.